Okay, so I'm just going to run down through the answer from yesterday's, and these are posted answer sheets. So just keep remembering, everybody out there, to make sure you're keeping the answers or your fixed ones or however you're choosing to do it for our quiz we'll eventually have on this stuff. All right, so a couple of review questions. Earlier this week we started on Tuesday with focusing on speed and velocity with circular motion. Yesterday was acceleration. Today we're going to move on to forces that occur when something's going in a circle. But going back to a couple of review questions dealing with some old acceleration stuff, because old stuff we learned about acceleration still applies to this new type of acceleration, even though it's on a circle. So number one, accelerating objects are, the answer to that, D, changing their velocity. A long time ago, very early in the year, we learned that the definition of acceleration was to change velocity. And number two, we actually had the same question a long time ago on an old study guide as a regular question. This is just a review one now. It says, identify 3 controls on an automobile that are responsible for causing the car to accelerate. Well, to be able to name those, and they're pretty simple, you got to be able to name the 3 types of acceleration: speed up, slow down, and change direction. All year up to this point, we've focused on speeding up and slowing down to accelerate, but just simply changing direction, like going in a circle, is another form. So that means 3 things in an automobile. Dominic, what's obviously how you speed up in an automobile? Gas pedal, right? Slow down is, and to change direction, exactly. Gas pedal, brake pedal, steering wheel. Those involve all 3 possible ways to accelerate. And some of them could be done both at the same time, right? You could be going through a turn and speeding up, right? Or you could be going through a turn and slowing down. The only 2 that can't be done at the same time. You can't speed up and slow down at the same time. But you could turn and do either one of those 2 at the same time. So we learned yesterday that the turning type of acceleration is kind of special compared to the other 2, because it doesn't involve speeding up or slowing down. So we called it centripetal acceleration. And the word centripetal meant towards the center, right? So let's move along with some specific questions on acceleration, and have to draw it in like we saw in the simulation of the ladybug the last couple of days. Number 3, a car that is moving in a circle at a constant speed of 30 miles per hour the correct answer is C, accelerating, since there is a change in velocity. Right? No, it's not because it's speeding up or slowing down. Constant speed means you're not doing that. But because you're turning, you're still changing your velocity. Not because of changing the size of it, but because of changing the direction of it, since velocity is a vector. So choice C is the correct one there. Number 4, an object that is moving in a circle at a constant speed has a velocity vector that is directed. So this was from earlier this week. This is where I'm going to flip back to the ladybug. Velocity is always straight off the circular path. We called that a special name, geometrically a tangent to the circular path. So that part of that question was kind of older from earlier in the week. But it also wants to know where the acceleration points. But because we call this centripetal acceleration, and so centripetal means towards the center, that means it points inward. So if we turned on the acceleration vector as well, you can see it always points to the middle. That's what centripetal means, towards the middle, towards the center. All right, number 5 basically just says, here's an object going in a circle at 3 different positions. And just draw we know it's going clockwise, so it's going around the circle like this. And it wants us just to draw these vectors that we just described. So if you got number 4 right, you should get number 5 right, because we're just drawing velocities going off tangent in a straight line from the circle. And remember, that's why if you let it go, it would fly off in a straight line, because that's where it always wants to go. But the accelerations point inward. So at every position, it should look like that. And again, that's exactly what we saw on this thing, right? All right, number 6. An object that is moving in uniform circular motion will definitely, they have definitely in bold, which means no doubt. All right? would have a large acceleration if it is what? Now here's the problem with why A isn't a correct answer. Moving very fast. Remember, it said definitely. You could have a high centripetal acceleration if you were traveling very fast around a sharp turn. But you could travel real fast, but have a really large radius turn and still not have that much acceleration. Okay? Because the formula I showed yesterday was v squared divided by the radius. And the way the math works out is, let me give you a real world example. A large passenger plane. Planes in general travel really fast, right? But a large passenger plane isn't built to take high accelerations like a fighter jet is. So, but they could be traveling darn near just as fast as a jet, a smaller jet. But because of their large size, it would be really bad for them to make a real sharp turn. So if you've ever flown on a passenger jet, commuter jet, when that jet is making a turn, if you notice looking out the window at all, they're big, huge, large radius turns. So even though you're going really fast, since the radius of the turn is so big, you're really not accelerating that much. All right? You are because you're turning, and you're accelerating centripetally due to that. Similar in a car. You could be going really fast in a car, like on the highway, 70-some miles per hour maybe, right? Or more. But you're not in a whole lot of danger of high accelerations on the highway because the turns are really large radius, right? So if you have a high speed, that doesn't guarantee you that you're going to have a high acceleration, because if the radius is real large, you still won't. All right. On kind of the same idea, just looking at a different aspect of that, B is not correct either. Moving through a very sharp turn. Now, yes, if you moved real fast through a sharp turn. But what happens in your vehicle when you know a really sharp turn's coming? What do? Slow down, right? Common sense tells you to slow down. You're probably going to fly off that turn, right? So that's why it doesn't guarantee it will. If you move around a sharp turn and definitely turn fast while you're doing it, you're going to have a high acceleration, and that's why you have a high chance of flying off the turn. So those parts, answering A and B wouldn't be correct, just because we could definitely put up a point that's saying, oh, here's a way we could do that and still be small acceleration. But if you turn real quickly at a rapid rate, if all of a sudden you're driving your car and boom, just turn the wheel, cut the wheel, and you're driving fast. So turning very quickly at a rapid rate, then yes, you're going to have a high acceleration, obviously. That's when, if you ever did it, maybe you're driving and, it happens sometimes, you're kind of not really paying close attention and a quick turn comes up and you didn't have a lot of time to slow down and you might just whip the wheel real quick. Even inside your body, doesn't it feel like it goes to possibly into the door a little bit and sways because you're free to move? And that's because of that high acceleration rate in that case. If you're in a jet that's obviously already going very fast and a jet maneuver goes to rapidly turn one way or another, they experience very high accelerations, really high in some cases, and that's why those jet pilots have to train for that before they ever actually go up and do it for real. Otherwise, they could possibly pass out while doing it. Those high accelerations could actually cause that. So the correct answer is C, turning at a rapid rate. And based on that, just a little, it's not a question, but it put a fact down here. The moon orbits the Earth, so the moon port pretty much goes in a circle around the Earth, or close to a circular path around the Earth. And it says here that the moon orbits the Earth with an average speed of just over 1,000 meters per second. That's really fast, right? However, the acceleration isn't very big of the moon due to that changing direction, due to that circular motion. The reason why, the radius around the Earth is huge for the moon. So even though it's going really fast, its acceleration isn't big because the R is so huge. It's like a big plane taking a very large turn, like we explained before. We could say the same about the Earth. The Earth orbits the sun, right? All the planets orbit the sun. So we have an extraordinarily long path around the sun, though. It takes us 1 year to go around the sun, right? It's 365 days. So even though the Earth is moving through space very fast, we don't really feel, like us on Earth, don't even really notice the acceleration because it's actually low since that path is so huge. Okay? If the Earth, like, something wouldn't happen, but theoretically, if the Earth all of a sudden, like, curved real quick for some weird reason in space, we would be in a lot of trouble because that would cause a rapid acceleration based on the speed we're already going. But luckily, that doesn't happen. All right, so got any questions on that one? Okay. So now we're going to move on to the force aspect of this stuff, and I'm going to show some demonstrations, just some basic ones on it. And I'm going to have a few little notes here that I'm again going to post at the end of class, so it's up to you. You don't have to write them down unless you really want to. Make them full screen. Alright, recently when we studied, let me get this thing out of the way for a minute. Recently when we studied forces, regular forces in the last couple of units before Christmas break, there was something we said to start forces, and that was if there's an acceleration, back then it was due to speeding up and slowing down, but will something magically speed up or slow down? Just all of a sudden for no reason? You're right if there's wind, but wind provides a what on the object? A force, right? So if there's like, if an object is just, we always said in the past, I'll use this thing, if I just sit this object or any object in front of me on the table, we wouldn't expect it to magically start moving and speed up unless some force acted on it, right? And sometimes some forces can be deceiving. Since wind is moving air and you can't see it, sometimes it may look like nothing's touching it, but when you think about it, something really is, right? So the main point is, we already described in the past that something won't accelerate magically. There's got to be a force. Well, we just learned and reviewed right now the fact that moving in a circle or even a partial circle is a form of acceleration. So again, that really means is something can't magically move in a circle, since the circular motion causes acceleration. When something moves in a circle, a force has to cause it. If there's a centripetal acceleration, there's got to be also, we use the same term, centripetal force that causes it. And the term centripetal force that I noted here in the notes, just is saying exactly what I just said. If there's a centripetal acceleration, it's always caused by a centripetal force. However, the term centripetal force is very generic. It just means some force that makes circular motion happen. So usually we have to, and this is going to be a big part of your study guide today, is identifying specific forces that can be centripetal. Typical forces that can make something go in a circle. Now, we could have a long list if we named every possible force that could make something go in a circle. But usually, everyday turning of objects, usually there's a small handful of forces that make it happen, that can make it happen. So I got a couple of things here for those of you at home. I'll make this full screen real quick. All I have on here is something I was using the other day in some demonstrations, but just for another reason right now. I'm swinging an object on a string. This is just a rubber stopper on a string. All right. So there's obviously centripetal acceleration because we got circular motion, right? There's also centripetal force because there's got to be something making it go in a circle, right? So what specific force is making this stopper go in a circle? What's directly attached to the stopper? Right. My hand isn't directly, but the string is. My hand's attached to the string, but what's directly attached to the rubber stopper is the string. And we learned in the past that we call forces on strings, ropes, and cables, things like that, tensions. All right? Tension is a specific kind of force. So when you swing something in a circle on a string, that means the centripetal force causing the centripetal acceleration, hence causing the circular motion, is the tension in the string. All right? And actually, when I spin it faster, it turns out that the tension even increases. And you can feel that when you spin it. But anyway, the main point right now is that the specific centripetal force is tension. So that's what we're looking for when we ask that. When I say what is the centripetal force making something go in motion, and your study guide is going to ask that, you want to identify the specific force. If it's on a rope, chain, string, or cable, the answer is going to be tension. Okay? We also, another common thing would be, this would be somewhat like a roller coaster loop, right? where we have a track, but instead of a roller coaster cart, I'm going to roll a ball bearing down it. And it goes around the track. What made this ball go in a circle? The track. If the track didn't go in a circle, would this ball have gone in a circle? No. It goes wherever the track tells it to. But the track doesn't involve a string, does it? So this time the centripetal force, it's not tension. We can't say it's tension unless there's a string, rope, chain, or cable involved making it go around. But this track is a surface pushing back on the object at every moment. And we defined a few weeks ago the kind of force that pushes back on something from a surface back on an object is known as a normal force. It's the same force you sitting in your chair right now. Your chair is pushing back on you with a normal force. Well, as this ball rolls on this track, it pushes back on it, forcing it wherever the track goes, which is why it's a normal force. So anytime you're on like some kind of track or something like that, like a roller coaster track that you're locked into it, then typically the answer is normal force makes it go in a circle. Normal force is the centripetal force. Another example, this one I don't have one to show in front of you, but we all can imagine it. When you go around a turn in a vehicle, let's make it real simple right now. When you go around a turn on a flat turn, okay, like in a parking lot, what's the only force holding you on a turn? Or a flat road, it doesn't have to be a parking lot. Friction, exactly. And if you're going through the turn safely and not skidding or sliding through the turn, specifically it's static friction that we talked about in the past, holding you onto that turn, not letting you slide through the turn. So any kind of, even walking or running around a turn, it's the same idea. Instead of tires on the road, it's your shoes, right? Because we all know if we are turning on, and all of a sudden you hit a patch of ice, are you going to be turning anymore? No, you're going to start sliding off the turn, right? That proves that friction holds you on and makes you go in a circle in that way. Now, just not going to talk too much about this, but when you're on higher speed limit roads, pretty much all turns are not flat anymore. They're banked. Especially, where do you see most of the highest speed turns? In most cases, not all, when you're going off an off-ramp on the highway, right? Because even though they have speed limit signs to tell you to slow down greatly, most people probably don't slow down to like the 25 or 30 miles per hour they say to slow down getting off the turn, right? And if they didn't bank those turns, you'd be in trouble if you didn't. Because most on-ramps and especially off-ramps are very tight turns, aren't they? Because to save room, to save money and to save room, they make them tight to go back off wherever you're supposed to get off there. But if they were flat turns, remember, flat turns, only friction holds you on the turn. So if they were flat and you came off going almost as fast as you were going in the first place on the highway, you would be flying off those turns left and right. There would be accidents like crazy, okay? Because friction wouldn't be enough to hold you on going at higher speeds. So what do they do to them? They bank the turns at an angle. And what that actually does is it helps bring in a normal force factor like a track does. And both friction and normal force help you through the turn, which means you could get through more safely. All right, so even if you're going a little too fast since it's banked, it'll help you. Now, even if you're going way, way too fast, banking won't even help. You're still going to fly off the turn. But it helps you go faster than what you could with just only friction holding you on. And taking that to the extreme, if you ever watch something like a NASCAR track, those cars go around turns at pushing 200 miles per hour. And if you ever look closely, they're extremely banked. NASCAR would be a very boring thing for everybody to watch if it was always just a flat track. Because they'd have to slow down to very slow speeds to get around those turns, since it's only friction holding them on. And that wouldn't be that exciting when they slow down that much, right? So extreme banking angles allow them to still stay like at very high speeds and still make it around those turns. But even they have to slow down some going into the turn from what they were going on the straight stretch, because still they could go too fast and still slide up the turn. So that's just some other examples. Another force, one other one that makes things possibly turn, I mentioned orbits on the last study guide with the moon going around the Earth, right? Things in orbit, well, there's not a string attached to the moon, right? There's not a track on the moon, right? And there's not a surface pushing back on the moon or anything like that. What makes the moon go around the Earth? Gravity. So in some circumstances, gravity can make things go in a circle. So in the right circumstance, gravity could be the answer to the centripetal force. All right. So gravity, friction, normal force, and tension aren't the only forces. I'm going to skip down here. But they're the probably four most common forces that can be centripetal. They can make things go in a circle. So I'm just going to note them in the notes here. Tension, normal force, friction, and gravity. So you're going to give a big chunk of the study guide. You're going to be given like a little table of situations, and you're going to have to write one of these four answers down to what is the specific centripetal force. Okay, and really the last thing to go over new today is just including centripetal force on my diagram. On that Ladybug simulation I was using, for whatever reason, it doesn't allow me to show the centripetal force arrow or vector, so I'm just going to draw it here in the notes. So let's say let's take it, pretend it's this rubber stopper that I was swinging, all right? And here's the path that it was going around. I'm going to put it at 3 different positions. Let's just say randomly here, here, and here. And again, let's say it's moving clockwise this time, all right? So we already know that the velocity of it, or already should know from earlier in the week, if I asked you to draw a velocity vector at any of one of these positions, the velocity vector goes off tangentially of the circular path like that. So I'll draw all the old ones and the new ones. And we again should already know that the acceleration vector points towards the middle of the circle since it's centripetal. So I'll call that A with the subscript C on it. But the force we already said is also centripetal. That means towards the center. Force is always directed in the same direction as acceleration. This might get a little messy looking, but I'm going to overlap this acceleration vector with the force vector, or put it right by it. Also pointing towards the center. Centripetal force, centripetal force. At any given moment, it's also pointing towards the center. The force always has to be in the direction of the acceleration, the overall force. All right, so all of that should hopefully help you answer the new questions. But like always, even if you're not sure, take your best guess and turn them in by tomorrow. The only thing for those of you at home, everybody's in here at home tomorrow. The only thing I'm going to post tomorrow is a video of me going over the answers to the study guide you're doing right now. So just go ahead and work on that the rest of the time.